All right, so we're going to investigate trig waves as our title, and we're going to jump right into this one here, which is like an investigation. So this function is periodic. It's also considered sinusoidal because it has a wave type to it. Okay, if it were to be like boxy like that, it would be periodic if it continued the same cycles, but it wouldn't be sinusoidal because sinusoidal is only a wave idea. Have they talked about that with you guys at all? The difference between those two? Okay, so there is a difference. You can be sinusoidal and you can be periodic and sinusoidal, but there's waves that are periodic that aren't sinusoidal. Okay, so what we have here is two lines kind of trying to outline what the amplitude of something is and what the period of something is. Okay, so A deals with our, I think it's amplitude, yes. So this white line, or sorry, this blue line here, let's put a value on it, okay, at 4.4. The amplitude of a function is how far, and I'm going to put a line actually right through the middle so you can see, no, not 90, 0. And let's change the color to maybe like orange. Okay, so the amplitude is the distance from the equation of the axis. Have they talked to you about equation of the axis? It's a line going right through the middle of the wave.
Yeah.
Okay, so for this one, there's a line right through the middle of the wave at 0. Okay, and the amplitude is the distance from the middle to the top or the bottom, and you can see the absolute value of it is 4.4. So it's the exact same thing. Okay, and they've called it this letter A. And you're going to get into transforming these functions, and you're going to find out that A is always the amplitude. We'll kind of make sense of that a little later. But that's what the amplitude is, and that's what this blue line is representing. The period, let's focus on the x values. Okay, the period of a function is from one tip. Okay, so let's say we measure from the two peaks here, from 0 to 3.1. That would be considered the period because that's how long it takes this periodic function to reach that exact same spot again. Right, so we can extend the period, our b value, so it says the period is 6.3, and you can see that's the distance from here to here, these two peaks. And it would be the same distance if you were to subtract the trough, so the minimum points, negative 3.15, and 3.15 adds up to 6.3. So you can measure anywhere along this wave, as just as long as you're reaching the exact same spot again in terms of period. Okay, so there's actually a whole list of trig functions, and I don't think you guys are going to deal with cosecant, secant, and cotangent. So we're just going to show you what these are. Have you guys dealt with anything in radians yet? No.
Not yet.
So we've kind of fixed what we were looking at before. So here's our sine wave. Okay, so we'll talk about some of the major features of a sine wave. The amplitude of the original sine wave. Okay, and the equation of the axis is running right through the middle, like I said before. So y at 0. Now let's turn it to orange again. So this is our equation. From 0 to the y value. So from 0 to 1, that's what the amplitude of this wave is. Okay, and your a value is actually like written in front of here, and in this case, a is actually equal to 1. Okay, so if you were to do any transformations, that's how you find out what the amplitude is. It'll make a little more sense when you talk about the transformations. The period of a sinusoidal function is actually 360 degrees, which is how long it takes to get around a circle. So from 0 to 360, those are the x values. That's where the period is. And you could have measured those from the peaks if you wanted. The difference between 450 and 90 is also 360. So you can kind of see here where you can measure from any of the same spots, and it's always going to be 360 degrees. That's how long the original period of one of these functions would be. Okay, so that's for the sine wave. Now, cos wave. Turn sine off. It's very, very similar. It has the exact same amplitude. Okay, the amplitude of a cos wave is 1. It goes up from the equation of the axis, which is at 0. It goes up 1, it goes down 1, so negative 1, positive 1, so that's your amplitude. And your period is still the exact same thing from 0 to 360, and you can kind of measure it anywhere you want along the wave. Okay, and the difference between them is going to be 360, so that's what your period is going to be for those. Okay, and those are the two most common wave type functions. And each of these would be important coordinates. Sometimes they'll ask you to memorize important coordinates on the original sine wave or the cos wave. These are the types of coordinates. So you kind of like just pause it here and write it down if you guys want to get all those down. The one that looks very, very different is tangent.
Whoa.
Okay, so tangent is a very different looking function. It does not have a wave, and that's because it has something that's actually impossible at some points. There's degrees that don't make any sense. So let's see if we can pull one out here. It should be
kind of looks like x cubed.
Oh, x, like x cubed. Oh, you're right. It does look like a cubic function. You're right. X is equal to negative 90. Yep. And x equals positive 90. So these are, I don't know if they've talked to you guys about what an asymptote is. So tangent would have a vertical asymptote at x is equal to 90 degrees or x is equal to negative 90 degrees. It'll never touch that. And the reason being, let's see if this calculator will do it, tan at 90 is infinity. It's undefined. Okay, it's not, so if you were to put into your calculator, I can even show on a calculator here, tan 90, this will be infinity, so the value is infinity. So that's why we don't have it ever actually touching. There's no y value for that point. Okay, and then all of these is similar concepts to it. It would take the actual repeating of this is a little different. It actually repeats, so if it was to be given a period, even though it's not a wave function, it repeats every 180 degrees. So a little different from cosine sine. Cosine sine are at 360. The tan is going to repeat every 180. So if I were to add 180 to 90 degrees, the next vertical asymptote would be 270. Right, there we go. And we have our next vertical asymptote. And you can kind of see the repetition from 0, that's kind of where the middle of tangent is, to 180. The amplitude, there really is no limit on a tan function. Because it reaches to infinity and reaches down to infinity, it's got an infinite amplitude to it. So you really wouldn't have a value for those ideas. Okay. And then you have the reciprocals, which are cosecant, secant, cotangent, but we're not going to focus on those. We're just going to kind of keep these. And I assume these are everything that you guys would actually deal with in terms of investigating any of these functions.